All right, I think we're gonna get started here. All right, everybody, so good morning. My name is John Hibbenid, or Björkus Dorkus, depends on where you meet me or where you find me. If you find me through Twitter, I'm so sorry. Welcome to a small talk I'm calling Hello Operator, and it's about specifically making calls for C, and not just any kind of calls, but the calls to put actual operator overloading in C. Now, before anyone freaks out, C hasn't actually put operators in the language yet, so nobody has to, grab their pitchforks just yet. I mean, I have to say that because I made a tweet jokingly about operators in C, and it ended up on a Reddit somewhere, and they were like, "Oh my God, he's going to put operators in C. He's ruining the language," which is how they say that about everything I do around C, but whatever. Of course, the reason why they're actually concerned when I make those kinds of tweets is because I'm actually the product editor for ISO, IEC, JTC1, SC22, WG14, which is a very long-winded way of saying the C committee, right? So it's my job to take all the papers that get approved, glue them together, and then make sure the specification that gets shipped out to ISO actually makes sense. And we actually just got done finally conforming to all of ISO's demands and polishing up C23, and that should hopefully publish sometime before the end of this year. It's going to be called C23, and we officially voted it to be C23, even though it's publishing in 2024. But that's just how that goes. So this is not really a talk about kind of contemporary issues. I mean, it will kind of go over some things that are present in current implementation in C and C++ about the way things work. But this is kind of going to be a talk that's more geared towards how do you design under those kinds of constraints, right? How do you walk into a language that's C that's 50 years old and then decide you're going to start changing some stuff, right? It's an interesting task. And we're going to see if we can do this so that we can put operators inside the C language. What would that look like, right? What would the syntax be like? What would the performance metrics, what were the design characteristics, right? How can we avoid certain decisions made by C and C++ and so on and so forth? So let's get into a little bit of that. While I'm talking about this, you're going to see some art. This was actually done by King Kismet. The sheepy character over there in the robes is actually a character representation of me. It's the character I have for my blog, the phd.dev, where I talk about a lot of this stuff and how I get people interested in C and C++ and optimization and standards and all this other fun stuff. So that's kind of like my blog character. And then the other person is actually more of a diehard C fan. He goes just by the name of Bird. But as you can see, he's a bird, but he's specifically a shrike. But they are, a person who is kind of a diehard C fan, and so you're going to be seeing some art from me kind of elucidating some of the situation. Specifically, the kind of situation I want to elucidate about is that operators are kind of this thing that everybody loves to hate from C, right? Everybody loves to beat on it. It's so infamous that James Gosling, when he was making Java, he was like, yeah, no, it's going to be kind of over my dead body if you ever think we're going to put operators in this language, right? And so, he made the very personal choice about not including operators in Java because he had seen too much abuse of it in C++. And I mean, who here has had to deal with abuse of operators and had to work in a code base where somebody made a DSL out of macros or whatever, and it's Hannah says she loves it. I mean, you're the author of CTRE, so probably, a little bit of bias there. But, no bias, of course. It's perfectly pure facts. It's great. It definitely makes sense. But, it's hard to overstate just how much of a profound impact C++ has had on the ability of people to reason about operators in languages, right? To the point that, again, it just gets such universal pushback in almost every sector of programming language design you go into. A little bit. I mean, some of it, but not quite. So it is very hard to talk about, right? So even if you try to convince people that, it would solve the problem, it would give you cromulent syntax, right? It'll do this, it'll do that, right? They're just kind of very much against it. And some of it seems kind of emotional, and some of it kind of seems like it's reasonable, right? If you've ever had to work in a code base where everything is put behind an operator, right? And you're this is it's your first time looking at it, that code just gets impenetrable, right? Like, why is the left shift being used here? Why is the increment operator between these two things? Like, how come you're using the less than sign, but this isn't a comparison? And how come isn't returning a Boolean? Like, what's going on here? It's beautiful. It's beautiful in some ways, but it's important in others. And again, beauty is kind of in the eye of the beholder. And as a junior developer being first introduced to this kind of code base with no help, maybe being exposed to operators in that way is not quite the gentle introduction you'd like into making things nice, And I mean, it's sort of things like this. Like, how could anyone possibly guess that, subtraction was going to be used for concatenation of two state machines, right? Not even plus, right? It boggles the mind. But, like, this is where it comes from. This is like the source of the frustration, right? Like, you have operations that you want to give names, that you want to, kind of perceive and understand when you read the code, but you can't because it's locked behind these operators. So you have to do a lot of code reading and a lot of maybe even debugging to get to a place where you actually understand, okay, this is what's actually going on in this code. This is what this notation means, right? It's not unlike when you have to learn math notation for the first time, algebraic notations and other things like that, but the benefit of algebraic notation in mathematics is that usually it's very shared, right? It's widespread, whereas the things that people come up with and cook up with in these code bases are very not shared and not intuitive to a outsider, right? But it does have some genuine appeal, right? Some people do like operators, right? They do want to see it, whether it's in C or in other languages, right? They try to push it into places like C and other places, right? So these are two proposals, N3201. They're the N, and then followed by 4 series of numbers is a N document, which is a document that is kind of officially put up for C to try to put something in the language, right? Make a fix, remove something, add something, so on and so forth, right? So there's 2 papers here that were very recent, right? 2022 and 2023, where people wanted to get some form of operators into C, right? And this isn't super new, right? We define operators for standard and annex math types all the time, right? So not just your ints and your floats and your longs, your doubles, but complex types, which is covered by Annex G as far as the C standard is concerned, imaginary types, but actually not for much longer because we just voted in a paper for C2Y, which is the eventual new version of the standard. I hope it comes out in 2028 or 2029, not 2030, that'd be too long. But imaginary types were actually voted out of the C standard recently because it wasn't seeing much use and the spec wording around it was kind of dubious and questionable. So we kind of got rid of imaginary types, but we kept complex types, which is in Annex G. There's also stuff from Annex H, which is the floating point interchange type. So you have your decimal 128, so your actual decimal floating point types. You have your float 128, your float 32x, which is your extended floating point, 32-bit floating point, and so on and so forth. And there's also some proposals that try to take advantage of this or try to propose this kind of stuff. So for example, if you've ever been very annoyed by the fact that C does not have wraparound, right? Wraparound integers, right? Or certain things that you would think would just be basic in the language to make things safer and easier. There was a proposal from a man by the name of David Svoboda who proposed something called N2683, which was towards integer safety. And so we actually accepted part of that proposal, but we didn't accept the part with the ckd_int_t that would give you a checked integer that would tell you if it accidentally wrapped around or overflowed or underflowed and stuff like that. But they're still kind of trying to pursue that. And so this is where kind of this interest in operators is kind of bubbling up from, right? That we have these plethora of types, and a lot of the time in order to make these types accessible, we have to inject them straight into the core language itself rather than kind of giving you the tools to do it yourself. And so there's this kind of tension between what users want to do and what they want to define, especially with their math heavy, right? If they're doing linear algebra, if they're writing kernels, whatever else, versus other users who aren't really all that interested in that stuff and they don't really want you to complicate the language, right? That's usually the complaint that comes out, making the language too complex, too complicated, by adding all this extra stuff on top, right? Of course, there's the more spicy, the more spicy way of looking at this, right? So this is Freya Holmer, who is a extremely talented graphics developer, compiler developer, foremost in her field, And Cheese does a lot of graphics programming, obviously, and so this is just some syntax. This is more of a C# syntax, or sorry, this is more JS syntax actually. This is using function calls to do a bunch of basic vertex math, and as you can see, it's very verbose, and some of the operations have to come in kind of in inverse order, in that you have to do the first operation on the inside most and kind of work your way outward to each subsequent operation, because that's just how the ordering ends up being for function calls, right? And so it becomes very interesting looking for a lot of the code you want to write, right? So there's kind of a back and forth between I want very cromulent syntax that represents exactly what I mean, right? That appeals to my domain, right? Especially for mathematics, right? This is huge for them, right? They want to be able to use multiplication and division and subtraction and addition, and they don't really want to have to think about all the complications around that. Whereas there are other people who are I hate that. I want functions. I want only functions. I want to be able to read every line and understand what's going on, and not have to look at any definitions and do any of that stuff, right? And so this brings me to this talk, right? Can we make this for C, right? So obviously there are proposals, there's all these other types, there's all these things that people want to do with it, right? There's both sides of the equation. Can we actually make operators in C? And that's what this talk is going to be about. And the way this talk is going to be structured is that we're going to start from a C++ system, right? So we're going to start from all of the things that make operators work in C++, or most of the things, right, that we care about, right? And then what we're kind of going to do is we're going to see if we can kind of backtrack and analyze and remove and cut away and think about and design our way away from the C++ way of doing things, and maybe into something that's more friendly towards C, right? So try to figure out some ways that we can make the feature set applicable to C without sacrificing some of C's core tenets, and hopefully allay people's fears about operators in the process while we're doing that, right? So what do I mean by the C++ system? Well, there's a specific set of systems that in C++ work together to kind of conspire to give you operators, right? That allow you to make operator plus, operator minus, operator divide, whatever. And there's about 5 of them. So you have your name or argument dependent lookup, right? So name lookup and argument dependent lookup. So when you call a function or call an operator, right, it goes and searches the existing symbols to find exactly the operators of the functions you're trying to call, right? You have overload resolution, which after you find all of the things you're supposed to be calling, right, which one is actually the one you want to call, right? So they're all named operator plus. There's 50 of them. Which one did you actually mean to do operator plus with, right? Then there's the implicit conversions, obviously. So okay, maybe you added an integer to this vector 2, but actually, we can promote that to a float, and so we're going to call the version that's vec2 plus float and make that work rather than forcing you to do a cast on the integer or whatever, right? So that's where the implicit conversions, constructors, things like that come from. Then there's destructors, and resource acquisition is initialization. That's such a mouthful of an acronym, but RAII, right? So the thing that provides safety and resource safety in C++, your general purpose undo mechanism in C++, right? And then you have references, right? The things that allows you to pass normal-looking objects without having to actually qualify them as pointers, and then you get a reference to it, right? Something that points at it but doesn't actually copy the value or whatever, right? It's just a transient thing that allows it to go down argument function calls and get returned and behave normally, right? So let's actually start with name and argument dependent lookup, right? We have a system that helps us find all of the operator plus we're interested in, right? So let's just take this kind of quick snippet of code. It's not very complicated, right? We have a namespace, mathlib. It's got a vector 2 in it. It's got a float x and y. This is the most basic vector type in the world, right? Nothing fancy. It's got an operator plus internally as a member function to allow you to add 2 vector 2s together, right? So do pointwise addition, right? So x gets added to x, y gets added to y, whatever. And then there's 2 free functions at the namespace level outside of the structure that allow you to add a float to the vector 2, right? And what that supposes is that it adds the float to basically both components rather than forcing you to create a temporary vector 2 just to say I want to add to both, right? And you do that for both the right-hand side and the left-hand side, right? And syntax is very simple, right? We have a quick main down here where we just make a vec2. We initialize it with x to 1.0 and y to 2.0. And then inside this kind of grossly parenthesized expression, we do v plus 3.0f, so we're invoking one of those plus operators. We're then getting the x of that and then truncating it to an integer and then returning it to main, right? So we use the value that we create, right? And so the question is, how do we find the function, right? There's 3 operator pluses here, and so we need to actually find the one, right? We're actually operating at the global namespace, right? We're operating inside function main, which exists in the global namespace. That's not in mathlib. So how does it know to actually go off and find that plus inside mathlib, right? How does it know to know that it has to get to that place? So the way it works is, I'm being very glib about this because in the actual C++ standard, this is a huge deal, and it's got 17 pages dedicated to just this is how you find a function that you're looking for, right? With these arguments and with this name under these circumstances, right? But in this case, it's very simple, right? It looks in the namespace of the type of each argument, right? So we're using a vec2 and we're adding to a vec2. So it's going to look in the namespace of vec2, and it exists in the mathlib. So it just looks in mathlib and says, okay, are there any pluses here that I should be interested in, right? And so it finds all 3 overloads inside the mathlib, right? And so it finds the member function in the type itself, and then it finds the 2 free functions in mathlib. And so that's the full set of functions that we look at. We've collected all the functions we're interested in, right? And then after that, we use types, conversions, orders, and more, right, to select the right function, right? So in this case, we're adding a vec2 to a float. So in very specifically, we want to look at we are trying to look at, oops, my bad. I believe I have accidentally gone too far. That's OK. I went way too far back again. Sorry about that. Let's say this is a real presentation that I'm already goofing up. OK, great. I did it right this time. So in this code, you can see that what we're specifically looking for is we're looking for this, right? We're looking for the vector2, the second vector2 plus operator plus that has the vec2 on the left-hand side and the float on the right-hand side, because that's what we're doing inside that call, right, that expression. But the problem is that none of this exists in C, right? We don't have namespaces, right? We don't have member functions. We just have regular free functions, right? Everything is at file or global scope. So when you're thinking about how do I put operators in C, a lot of that name lookup stuff doesn't mean anything, right? So this is kind of a C version of this, where instead of having a namespace, you kind of just prefix the vec2 with a quick thing, whatever. So in this case, it's mathlib, so we're just calling it ml_vec2. You're not allowed to have member functions, so everything is just there. And then you have to have operators, right? All 3 operators kind of exist in the global scope, because that's the only place you can declare functions, right, in C. So this isn't real syntax, right? This is just me taking mathlib and saying, okay, now that we're working in C, what do we have to get rid of to actually get closer to something that's working that would be viable for C, right? So we had to strip the namespaces because we don't have it, unfortunately, right? We have to strip the member functions, and so that moves that function outside. And then now we just have these kind of free functions with the name operator plus, right? And so in this case, now we don't have to do any lookup because all of the operators are now in scope, right? So they're just all in the global namespace. So when it comes to name lookup, I just say, okay, what are all the operator pluses in the global namespace? And that's it. I'm done. Right? That's my algorithm, right? So I don't have to I don't have any quirks for, okay, look in the type, look in the actual, class itself to see if there's a member function there, or a friend function, or a ADL found hidden friend, which is just there's so many different steps in C++. It's interesting. But in this case, it's very simple, right? There's 3 potential operators, the global scope, right? This is very C-like. It's just free functions. OK, right? So we've got that part down, right? We managed to make name lookup a trivial, non-issue, right? This is just how every other function works, right? You find the function that you're calling, and then you call it, right? And this actually gets us to what Jacob Navi was proposing in N3051, where he wanted to have operators. The problem is it doesn't quite get there, right? Because if you look at the previous code that we were running, there's still references in here, right? And C doesn't have references, right? And there's a bunch of other kind of subtle things. We don't have the operator keyword in C either. So we're not quite there yet, right? We haven't actually gotten to something that works in C by itself. So we now have to kind of think about like what else do we need to address or get rid of or tweak in order to make something work in C, right? So back to the system's underlying C++ operator overloading, right? We've kind of taken care of name and argument-dependent lookup, right? Everything's just in the global namespace. They're all free functions. That's the only thing we have to look for. Great. We know how to do that part in C. Now we have overload resolution, right? So you have a bunch of functions. You need to figure out which one of these functions you're going to call and do something with, right? So that takes us to this part, right? Overload resolution, figuring out which function to call, figuring out how we're going to do all of this. And so this was a very fun thing that Jacob Navia's proposal also did, right? So as you can see here, we've stripped off the references because, we're in C, we don't have references, right? So now we're just passing everything by value, which isn't a big deal because it's just a struct of two floats, right? So we're not like smashing the stack or something by not using references here, right? So this is like a very simple case, right? Most of the time you'd want to pass most of the stuff by value anyway. So we got rid of the references. We have the operator plus, and now this actually looks a lot like what Jacob Navia had in his proposal when he wanted to propose this to C, right? So his proposal was, listen, let's just add operator as like a kind of funny identifier that goes there and then allows you to put the symbol there that defines it, and then we can have the return value and our arguments there, and it will just work that way. And it works pretty much exactly the same way as C++, but we have an issue, right? How do we tell these three things apart, right? If you've ever looked at C code, right? If you ever looked at C code, you ever looked at C++ code, you ever looked at the generated assembly, this is an example where I've taken some C++ code that had an operator plus for an int 128t that I defined, and an int 256t that I defined. And what you see is that the function names here don't look like things that you would recognize, right? It has all these jumbled symbols in it, right? So there's like ZPL, 8 int 128t, you see the type name in there, and then there's like an S underscore, right? And it's like, what is all of that? And this is what's a process called name mangling. And name mangling is like a foundational feature in a ton of languages. Like Rust has it, C# has it, C++ obviously has it, and many, many more use name mangling so that even if you have a function or several functions with the same name, your binary, your actual code that gets compiled can tell them apart. And the way they tell them apart is by basically injecting types and other information from the function signature into the final label in the assembly that gets for the generated code. And that means that there is a one-to-one relationship between every function that exists in your source code and the actual binary that appears here. So even though all of the functions technically have the same name, the implementation mangles that name with type information and other stuff to make it distinct, each one distinct from the other, right? And so this is kind of what C++ does in order to make sure that it can have all these functions with the same name, right? This is the binary side of overload resolution, right? So there's the front end side where it actually picks the function that's going to call, but then when it actually generates the code for this, it makes sure to put down here a label that is completely kind of divorced from the actual name in the source code, right? Okay, I think I haven't lost anyone yet. And so this is kind of bad for C, right? And so this is kind of a quick snippet of C++ code that's using extern C to demonstrate. But in C++, you can see that like the name is fully mangled, just like it was in that last slide, right? So, Florba Warba that takes an int and a double, right, gets its name mangled. So you see Florba Warba is in there as part of the name, but then you have these extra things like the I and D at the end, which stands for the integer and the double that you're passing in as a function, that you're passing into the function, and then the Z12 in the front for additional mangling that this implementation does. Meanwhile, for the extern C of the Florba Warbo, which is an O at the end, there's nothing there, right? It's literally just the name. Like the label in the assembly is literally just the name that comes from C. And so when you're talking about how do I differentiate these three operator pluses, C doesn't have any mechanism for that. It doesn't have any understanding of that. No implementation has any understanding of this, right? Now, obviously, if you're talking to Clang or GCC, right, they pack the name mangler that understands how to do this stuff, right? So C can still technically talk to C++ and vice versa because they have the mangling and they can understand that sort of thing. But if you go to, say, TinyCC, if you go to quick C, if you go to chibi CC, right? If you decide to go to the Serbian guy who's holding up his entire local compiler economy with his 1C compiler, he doesn't have any of this, right? They don't have any of this stuff. So it sort of violates the fundamental tenet of C, right? That what you write in the program is the thing that appears in your binary, right? And so this is kind of like a very sacred tenet because it also powers a lot of FFI, a lot of foreign function interfaces, because a lot of people will generate C code from like Zig or Rust or Odin or Java or whatever, knowing that the names they wrote in the source code are going to be basically what exactly appears in the binary. And that means that they can write reliable foreign function interfaces, right? And this is how C kind of becomes the glue language between all these others, right? Because they don't have any of this name mangling going on, right? And even though you see the name mangling here, it's actually different for almost every single implementation. Every single implementation mangles their symbols differently. MSVC has a wild name mangling. GC and Clang kind of share it, but it depends on the platform you're on, depends on what you're compiling for. It can change it up. Other people have their own very interesting ideas for how they should do name mangling. And so in C++, it's kind of really a wild, wild west when you get down to the binary level. Whereas in C, right, you write, Florbo Warbo, you get Florbo Warbo every time, everywhere, or just about everywhere, right? You might get like an additional underscore in places for like there as like a differentiation mechanism, but otherwise what you see is what you're getting out, right? So this is what Johnson's N3201 was trying to do. He was trying to do operators without overloading, right? A way of specifying operators without having to do the overload. Now, from Jacob Navia's standpoint with his paper, with just using the operator plus, the actual keyword operator and the plus, he said, well, it's just implementation defined, or we'll define a mangling in the standard and then we'll do that, right? But that's kind of in contention with C++, right? If you define a mangling by the C standard, right, whose implementation wins? Is it MSVC's? Is it Clangs? Is it GCC's, right? Who gets to define what the mangling ends up being, right? And so it kind of became difficult, right? It also becomes hard to name a function, right? If you don't know what the mangled name will be, how do you form a function pointer to this thing in C, right? Like we don't have the same kind of mechanisms and castings and whatever to get at the function pointer, so how do you name a function pointer with operator plus, right? And so it was very kind of convoluted, and this is where Jacob Navia's proposal kind of broke down in the committee and in communication when we were trying to discuss it and talk about it very recently, as far as I think back in January. Marcus's standpoint for N3201 was, what if we designed it so that we didn't have this problem? What if we made it so that this wasn't a thing that we had to worry about, right? And so this was also the standpoint I had, because I was also cooking up a proposal for this, but I hadn't actually published it yet. And so the idea is that maybe we, instead of tackling this from a position of, well, maybe we'll just define a mangling, what if we just didn't have mangling at all, right? How do we, and now it comes into question, like, how do we do that? How do we fix this, right? But first we have to kind of address the two warring sides here. So this big snake-like fellow is Sendine, and then of course we still have Bird from before. Sendine is kind of on my side, actually. He loves operators. He wants operators. He's actually a diehard C enthusiast, but he wants operators. He wants to see C grow and change and do other things like that. Whereas Bird is more of your typical conservative, I want function calls only. That's the way this should work, right? So when you're looking at this, right, you have these operators, and you want to kind of separate the operator itself from like the actual function that defines like the mangling and everything else that goes on behind the scenes, right? So, the thing that's the core problem here is that the actual behavior of operator plus is kind of locked behind this unnameable operator, right? You can't call these normally. It locks out the people who want functions. And yes, obviously overload resolution provokes all the naming issues I talked about before, right? So we kind of, those are like the things we have to solve with our design, right? So first off, we're gonna go back to the functions, right? So here's the functions. And this is mangled, but it's like hand mangled, right? Like we're writing ML vec2 add. We're writing ML vec2 add f. We're writing ML f add vec. Like we've done mangling, but it's our mangling, right? We put this in the source code, we put this in the header, we implement it in the C file, right? And so it is a mangling, but it's one that we chose for our library with our namespace, with our scheming, whatever, right? So we've got the functions, right? And this makes the function people happy. They're like, oh yeah, I'll write this all the time. Screw those operator people. I'm going to write this all the time, right? But we still want the operators. So what if we still allow you to declare the operators, but we decouple the function call and the function declaration, the function definition, if we decouple that from the operator itself, right? So here's my syntax that we're just like the fancy syntax I've just kind of made up right now, right? And hopefully it's not too hard to understand, but of course I'm going to walk you through it. In C, we have the horrible, horrible, horrible thing that we don't really have a way of claiming our own keywords, and we don't have context-sensitive keywords. So what happens is we usually have to do the underscore capital letter fix for all of our keywords. So that's why operator here it looks so weird. We have to spell it in this kind of ridiculous way in order to like not collide with people who are existing in the real life, who have written code that has the identifier operator in it, which sounds silly, but people do that. So here we have underscore capital O operator. I'm just going to call it operator from here on out. But underscore capital O operator, and then we have an open parentheses. And what this list is just this list of arguments into this weird statement, is that it's just basically telling what kind of operator we're defining. So we have an operator plus. It takes two vector 2s, right? Two float and float types. And then we want to bind it to mlvec2 add, right? So we're creating this association between this function call and this operator, right? So there's a plus operator, and it will call, hopefully, mlvec2 add, right, using this syntax. Anybody lost? Have I lost anybody? No. Great. OK. Wonderful. Same thing for the other two operator declarations, right? We have an operator plus, but one is with mlvec2 and float, and the other one is float first and then mlvec2, right? And we're just binding it to each of these functions, right? So we're name mangling, but we're doing the name mangling ourselves, right? And so this is what I say to those people who want to have either operators or either functions. I come in there and I say both, right? Much like the tabs and spaces debate, I also show up and say both, and then I get, and then this happens to me, right? I get beaten up, because they don't really want to share. They think that it's an affront to nature. I'm ruining the language and I'm taking things away from them. But I want to, hear me out, okay? Before you beat the crap out of me, hear me out, okay? These two pieces of code do identical things, right? So we're creating a vector, right? Similar code to before, right? Literally the same code as before in the top one, right? We're using the operator. We're doing v plus 3.0f. We're taking the member of x and then casting it to an int and then returning it, right? But in this bottom snippet, we are doing the exact same thing, but we're using the mlvec3 add f, right? We're using the function we created. And the idea is we can have both of those coexist at the exact same time, right? Without actually forcing you to pick between the two. And the reason you do that is because the design forces you to make them both available, right? So both of these will compile because you've made a design that gives you not only the function calls by forcing you to pin the operator to a function call, but then also gives you the operator that will always translate to that function call, right? And so both people who want to write the operator code but also write the function code get to actually live in the same code base, right? And they don't have to necessarily be at each other's throats, right? Now, obviously, if you have a senior person, right, they might try to force their opinion about how the world should work, right? We only use operators here. None of those garbage macros or function calls. This is a wholesome, clean code base where the code looks normal. It looks like it came straight out of the math textbook, right? Those kinds of people. Then you have other people who are like, no, we write function calls here. Everything is a function. It's readable. You make temporaries, and you understand everything about the code, and that's how we do things here, right? And that's up to a matter of style. But the whole point about the design is that the design enables you to pick, right? So instead of being like James Gosling and saying no operators for anyone, or instead of being like C++ where we have IOStream operators like, well, actually, you can't actually call a function to do this. It's actually all hidden behind the left shift operator, and that's how you're going to do your reads and your writes for IOStreams, right? This design enables you to pick the one that you want, right? So there's some times where you're taking a formula straight out of a paper, right? And you want it to look as close to that paper as possible, right? Or you're working with scientists, right? And they're usually working Fortran or something else, but you dip them into C, and they're like, okay, well, how do I write this code with these vec2? And it's like, well, you have to write a bunch of functions and stack them all together and make sure you do it in reverse order, because remember, you have to evaluate the arguments of the first function call and then kind of work your way outward, right? So you have to teach them all of that, and they get like annoyed and like, what is this garbage? Like, why am I writing it like this? Give me a break. But the whole point here is that the design kind of enables you to pick one or the other at your leisure, right? And so by forcing this, you're able to kind of prevent the war that breaks out, usually when it's like, well, I want operators, oh, I want functions. And so you can kind of reach this kind of middle ground here by just getting rid of the overload resolution problem, and by making that linking, that connection between the operator and the function explicit, right? So now anytime somebody sees a vector2 that's being added to by a float, they know where to find the operator and then where to find the function call from that operator declaration, right? Before, you'd have to go to the operator and then just start reading the code, because the operator was the definition, right? You fuse the two things together. That's what C++ did. And many other languages like C# and et cetera also did, right? They kind of fused the concepts together. But by doing this separation, you can avoid a lot of that headache, right? And so it's a little bit of an extra step. Obviously, you have to declare this extra like underscore capital O operator nonsense, but by separating the two, you've now effectively eliminated the problem that came with the original issue in the first place, right? And so now we've successfully taken care of overload resolution. And now there's like 3 other systems, but they're actually much smaller systems, so we don't really have to get too deep into it. But having done that, right, we have the problem of implicit conversions, right? So in C++, right, if you have a integer, right, it might get converted or promoted to a float and then used with this vec2 operator, right? Mostly for convenience purposes, right? A lot of these implicit conversions and promotions, integer promotions, et cetera, are purely for convenience purposes, right? The problem is that implicit conversions are like basically the root of all evil, right? Which I know it's, usually we're like, oh, it's inheritance, it's the base class of all evil, right? If you're Sean Parent or something. Usually, there's other people who have very specific ideas about what the horrible things you can do in C++. But if you talk to Jason Turner, who I think is he, hey, Jason's here. Implicit conversions, he says, are the root of all evil, or most of it in C++. And I mean, having programmed as much as I have, he's kind of right. He's kind of cooking here, because I've had to deal with a lot of like crazy overload sets and everything like that. And usually the thing that breaks the overload set or makes things go haywire is that there's some implicit conversion somewhere like, oh, this string view gets automatically constructed into this type, and that's why this whole thing blows up in your face, and that's why you have a dangling reference and whatever, and so on and so forth. And a lot of that comes from implicit conversions, right? Similarly, Sean Middleditch, who is I don't know if currently, but worked at Blizzard, working on a survival game, senior programmer, tons of experience under his belt. He actually made his own language, and he put implicit conversions in them. And he says it's his second or third largest mistake of his whole career, right? Doing implicit conversions, right? The Rust folk also got a whiff of implicit conversions from C++, and some from C, and decided to like never have any of them in their language at all, right? If you try to add like a 32-bit integer and a 64-bit integer, it will like force you to cast one of those. Like you can't even just like do that normally, which is a little annoying. Like it's definitely annoying, but it's a pain. And so in this design, we're actually going to not deal with it, which is bad in a way, right? You kind of want it to work because you kind of want that simplicity to kick in. You want floats to convert to doubles and vice versa or whatever. But in this case, right, as you can see from the code here, right, we have the operator set up from the exact same operators as before. But if you try to add a 3.0 instead of 3.0f, which is a double versus a float, if you try to add the doubles to that, it just says, I don't know what you're talking about. There's no operator for this. I hate it. Question?
But that would change the behavior between using the function, which would implicitly convert, from using the operator, which would now disallow implicit conversion, right?
Yes, and the reason it's like this, the reason the behavior is like this, is because specifically, and this is about the next slide, about the lookup algorithm, right? When you get to the place where it's like, okay, I need to consider a large variety of stuff so that I can pick the right operator, right? Because remember, there's still, even if we've gotten rid of overload resolution, there's still like I have to pick the right operator from this list of operators. If you get into conversion issues, then you have to wonder like, okay, which one of these am I going to call? Now, in the case that we're seeing here, like, this is very simple, right? Clearly, it should probably pick the float one, right? Like, even if it's the double, right? It's 3.0, a compiler that's, not even modern, like, relatively, like, not even new, like, from the early 2000s can tell you that, this 3.0 is small enough to fit in a float. It should probably work out just fine. There's no errors and no, warnings you'll get, right? It should just work, right? But the reason we have to do this is because we want to do that exact type match, because again, if you had the same code, but you had an operator plus for double, then it's like, okay, well, should I pick the double one? Or if you had an operator for long double, like, should I pick that one? Should I pick this one, right? You start to get into these arguments about like, which conversion am I supposed to invoke? Which one am I supposed to match? And so that's why kind of, at least for the first blush of this, we're not dealing with implicit conversions. Like, there's no implicit conversions, it matches directly or it doesn't, right? And the good news for doing this for function calls, like you said, obviously you get back those implicit conversions in some case where you get argument promotions to double and things like that. But in the case of the function call, right, you've kind of made it explicit that you're calling a function again. So like, the trade-off is like, okay, like you've asked for it, so like you get all the function-like behavior you wanted. But for the purposes of the operators, right, and for the purpose of making sure that finding the right thing is easy, we're kind of just doing an exact type match only. Well, yes, and so there are very interesting things you can do with exact type-based matching, even though it will get annoying to do it that way, right? Again, here I have to basically add 2 whole extra things just for double, and then I have to add 2 extra operators for double, and it's annoying. But one of the interesting things that you can do when you have exact type-based matching is that you can kind of control the promotions you do or don't do, right? And this gets very important when you have like mixed integer addition and things like that, right? Obviously for vec2 it's kind of silly, but for when you're doing like, I'm going to add this int 256 to this int 128t, you could say, okay, well, do I want that to happen, or do I want to actually make it be an error, right? And so you can decide for each mixture what to do, right? Obviously, it's annoying, again, to define it all out, but that's what you could also just do a cast and it would work just fine. I think there's 2 questions.
I think Jason was first.
Oh, 3 questions, sorry.
Is this consistent with how the underscore generic thing is that no one actually uses from C11?
Yes and no. So in C2Y, we added a new feature, actually. So if you have generic, and the way generic works is you put underscore capital G generic, you open an open parentheses, then you put an expression, right? Something that eventually computes to some kind of value that'll eventually give you a type, right? It's basically like size. It's kind of like size in that way. You can throw a expression in there, and it'll basically compute the size. Well, this will just compute the type. And then that's what it'll use in this underscore capital G generic thing to then match on a series of branches. And then what C2Y did is that we actually added exact type matching if you wrap that in type of. So if you pass a type into generic, it'll do exact type matching. And so it won't allow, yes, it won't do conversions in the case if you use the type-based matched, but it will do conversions if you use the normal generic. But it won't do the normal implicit conversions. It will do what they call L-value conversions, which is like float can be, no, not float can be proto. It's like arrays are decayed to pointers, and there's like a couple of the things that happen, like qualifiers get stripped off. So if you want to do underscore generic to like match on an int versus constant, you can't do that with an expression. You have to use the type-based version, and that will allow you to match on int versus constant, because it won't actually, because again, L-value conversion, the fancy standard term for this is that it strips off qualifiers, right? It actually gets rid of your const, your volatile, and then any implementation defined stuff that you have in there, like kernel address spaces or whatever. Yes, so you can do exact matching in C2Y with generic, and funny enough, it was so popular, the extension when they made it, it was so popular that they actually backported it to all the other standard versions. You'll get a warning on pedantic code if you try to use type of around an expression in generic to do exact matching, but if you don't have pedantic warnings on it, you can do that all day, and you can get the exact matching. That was actually a case where implementers actually, rather than just complain to the standard, they actually like implemented it themselves and then got it through, and then that's why it sailed through the committee in one meeting and everybody was happy. But yeah, so that answer your question? Yes. Okay. Yes?
So in this case, couldn't we just have 5 operators for 3 functions? Just explicitly say if you have double and vec2, then just use mlf at vec2 to basically force the compiler to do the conversion that it would do anyway for the function?
Yes, that is something that you can do. I don't explain that here, but yes. Because I am going to be proposing this to C eventually, right, I have to write all the spec and all the wording, and that's part of it that's in there. It's that you can write 3 functions, then you can kind of cheat your way into doing conversions by just defining a bunch of operators that will call the function that will just naturally do a narrowing conversion or whatever. But again, to be explicit, like you have to write it all out, right? So if they're unrelated types, right, you'll have to write out all the functions yourself, sure. But yes, you can write 3 functions and then just add the double ones that call the float ones or whatever, however you would like to go about that. Okay, any more questions?
I have a question, but it was the
Same question. Okay, all right, great. So, is there room for argument promotion or integer promotion, which is kind of what's been noticed here? And it's like, yeah, perhaps there's some room for that. But again, we're not really going to get into it. We're kind of just going to stick with exact type-based matching because that's kind of the simplest. And the good thing about exact type-based matching is that later on you can kind of tack the promotion stuff onto it later, and it's like not going to break anybody. It'll just make code that wasn't working before start working again. So this is kind of like how you do standardization, right? You convince people like, oh no, we're making a small system that won't break anything, and then you're like, we'll add it later, and then maybe you get to adding it, maybe you decide you're going to go horseback riding into the mountains and never come back. But that actually takes care of implicit conversions. But now we get to a very interesting one, which is destructors and RAII. This one is actually a doozy, right? Because this system is actually very hard to replace. But first, before we get into that, let's do a brief overview. I'm sure most of you know about this. But RAII, what is it, right? It's in C++, it's the ability to make an object that will capture something, hold on to that resource, and then when the object dies, it invokes its destructor. And you can do anything in the destructor, right? So the constructor will be able to create something, and it sets the classes invariants and the structures invariants and set member variables and whatever else it needs to do. And then when the destructor invokes, it's supposed to be an undo mechanism, right? So if you allocated something, you're supposed to deallocate something. If you grab the file resource, you're supposed to release the file resource. Or if you grab a mutex, you're supposed to release. If you lock the mutex, you're supposed to unlock it, so on and so forth, right? It's a general purpose undo mechanism. That's exactly what RAI is, right? You do something here, you can undo it down here, right? And it's guaranteed that if you successfully do the thing up here, by the time you break out of here, unless you call like long jump or something, or do like a inline assembly to break out, right? You're guaranteed that any way that you can return or break or go to out of that block, that variable when it's destroyed will call its destructor, right? So again, it's a general purpose undo mechanism, right? We don't really have that in C. It's also something I'm also working on to fix, but not quite yet. So why does this matter, right? So let's imagine like we have a big int structure, right? A big int structure in C. And it has some unsigned long data in a std vector, right? So this is basically just a growable array of data. We can we can put stuff in it, and you can also add, and we just have this big int operator plus add, right? So this is C++ code, right? So what happens if we try to do the same thing in C, right? So, let's say we have an allocator of some kind. We're trying to replicate what the feeling for what the std vector is. We're kind of cheating because we don't keep the size here. We're using other ways to track that. But we have an allocator. We have the data. We have a pointer to the data, and we're going to kind of allocate the data in the structure. We're going to keep track of it, and then we're going to destroy it when we need to, right? So we have a big int, make big int, which just takes an allocator, and then we take an unsigned long log of an initial value, right? Very simple stuff. And then we have a void destroy big int, right? Where we take a big int by pointer, and then we just kill the insides, right? We destroy the data, we zero out the allocator or whatever. So then we make an add function, right? So remember we have that function operator split. We have the big int add, and then we have a big int add operator. That's an actual plus that we can use to do this stuff, right? So let's try and use it, right? So we have limits.h. We're going to make 2 big ints, a and b. We're going to make one that we have some global allocator somewhere just called alloc. We're going to take 3 integers of 3 billion, and we're going to also take ulong max for a and b, and we're going to make big ints out of those, right? And then we have big int c, where we do a plus b plus a, right? And then, to make sure that, we're good citizens in C, we always clean up our stuff, right? So we have big int destroy, C, B, and A, right? So we've cleaned up everything, we've created a bunch of stuff, we've done some temporary work, and we've destroyed everything, right? What is wrong with this? What is wrong with this image? What is wrong with this code? Yes, there is a big int that you cannot see, right? Because we do A plus B plus A, we have created a temporary. And this temporary exists right at that line, right at the A plus B plus A. So whether you do B plus A or A plus B first, you do that first, right? You do that binary operation first, because again, you do two at a time, right? So you do A plus B, you get a temporary. And so we're just going to kind of annotate this with the double underscore C, like pretend this is generated code, right? So we have a big int of double underscore C0, and that's A plus B. That's our first temporary. We get a big int C, which is the thing that was in our original source code. We do double underscore C0 plus A, right? And this is actually kind of like what my compiler that I wrote was generating, right? We have this generated code that does the next step that finally assigns to C. You do C0 plus A, right? And then you destroy all of the big ints except C0. C0 is still there. C0 still has data. C0 has allocated. And now you have a memory leak because you've attempted to use this data structure that allocates its own data, but actually didn't properly destroy itself at the end, right? And so this is the whole purpose behind destructors and RAI, right? Because the object itself has a concept of when it goes in and out of scope, it can successfully call big int destroy on itself, right? But we can't do that here because this is C. We don't have that mechanism. Now, there are many ways to handle this, right? You could use an arena or specialized allocator where you mark the beginning of a block and an end of a block, and so everything that's allocated between the two markings just gets obliterated when you go to the end of the block, right? There's all sorts of techniques that people use very frequently in C, specifically around arena allocators, right, to solve this problem, right? Garbage collection and ref counting style types are also available in C. They do this a lot, actually. If you go, for example, in GCC, the literal code base itself, they have a huge garbage collector, right? Chrome with Miracle Pointer, it's a C++ code base, but they have a garbage collector that's sitting behind it stuff that does ref counting and everything else, right? A lot of large C and C++ code bases will literally rely on a garbage collector or something of that nature to kind of make these kinds of problems just kind of quietly go away. Obviously, a lot more in C than in C++. But none of these solutions are really as automatic as you have them in C++, right? In C++ with Chrome, with the Chrome code base with Miracle Pointer, right? All of that stuff happens in its constructors and its destructors, and that's how it knows what to do, right? Whereas in C, you have to separate that from the object itself because you can't attach that information there. And I hate to be this kind of person myself, but is this really a hidden blessing, right? So it naturally encourages operators for simple stack-based types that don't do any allocation, and it naturally discourages complex heap-based types, right? And so maybe that's a win-win for the C community, right? For the C++ community, they'd hate this, right? They'd be like, this is awful, I hate this, I want my big int type with my data inside and everything just beautiful class, it's all encapsulated and everything's beautiful and perfect, and I have private with all the members and public with a beautiful interface, and they would hate this. But the C community, right? Maybe they'd actually prefer it this way. Maybe they'd prefer it if they, you have to go the extra mile to make an allocator work with an arena allocator or whatever, just so you can use these operators, right? So it's not really a solved problem in C, right? Obviously, because we don't have objects that can track their own construction and destruction, we can't really solve this problem, but maybe that's just fine for the C community. Maybe that's the only things they want are vec2s and they don't want big ints, right? Arguably, that's not true because you can see C libraries where they do big int things, right? And they have big int, big int structures and everything. But this is kind of like where we're at right now. We can't get a guaranteed fully safe operator feature that also works in this way because of these temporaries that are created, right? Okay, so that kind of takes care of the destructors and RAI stuff, right? We're kind of just saying, well, it's a win because, C, yay, which is a bit silly, but that's kind of where we're at. So now we have references. And references are a bit interesting because they're basically just pointers, but they're not supposed to be null, right? And that's like the big sell. But it's also a little bit more important than that, right? References were actually introduced into C++ very specifically to help with operators, right? So when you have assignment operators and things like that, you were supposed to, kind of use these references so that you aren't constantly copying, right? they also gave shape to existing C syntax, right? So in C, you can do something like pointer, and then index it at an ID at an index, and then set it to 5, right? And that's like this is like technically a reference, but like you can't hold the thing that comes out of pointer subscription with by IDX, right? You can't actually touch that thing. It's not real, right? Like you have to either directly assign into it, or you lose the ability to like assign into that slot again, right? If you can't hold onto the reference, right? But in C++, you can. You can make an int reference to pointer IDX, and then you can hold onto that int reference and start doing stuff to it, right? And it'll work naturally, right? And that means you can pass it into functions and return it and stuff like that, right? So how do we handle this for C operators? Well, we actually just do a little bit of a kind of a hack. And not really a hack, but like we have references in that we have pointers, right? Pointers are technically references, it's just that they can be null. So obviously people try to avoid them when they don't have null in the mix, but we don't have references in C. So what we do for C is that, well, we'll just have operators that take things by pointer, right? So that in that way, if you have a very large structure, right, you don't have to kind of keep copying it all along the stack, right? Now, obviously, any optimizing compiler will see that you're copying this huge, structure on the stack and kind of working on it over and over again, so they'll kind of try to reduce the number of copies. But it still would be nice if you, the programmer, had control over that. The same way in C++, where you have references, you can control that very explicitly by just writing the operators the way you want to. And so the way we're doing this is you have to write another function, because of course you do, because this is C. But we write another function, mlref_vec2add, and this one takes the results, the left and the right types, all by pointer, and, it should actually return void, my bad. But the operator declaration for this just has the same stuff, except that right after the plus, we have a little ampersand. And what that means is take the address of the arguments and temporaries that we're passing through these functions, right? And so that allows you to have these, kind of various temporaries and prevent having a constant churning of the stack when you're making a bunch of operations. Yes?
Can you do it for only one argument?
What do you mean? Oh, only do it for one argument. No, I have not designed it like that. The problem with that was that it was a little bit complicated to specify which was meant to be the pointer and which was not meant to be the pointer. It was kind of a headache to figure out how to do that exactly. There are some syntactic options I can use to get that, but it has like diminishing returns, right, almost. So either you want them all to be a pointer or you don't, and that covers like 90% of use cases. But like there are cases where it's like, okay, I just want the arguments as like values, but then I want a reference to the result, right? So I can just write into the result directly. But the proposal I'm writing is going to cover that, at least not at first. There is thankfully room to grow for the proposal I'm writing so that we don't actually have to suffer that. But that's kind of the idea behind how this works. And with that, that's a full design, right? We've managed to actually knock off every single kind of thing that comes with C and kind of create like a sort of working prototype of this thing in C for how you would have operators, right? Without name mangling, without overloading, without name lookup, without all these other things, right? And so now that we have this full design, I was, in this presentation, I was kind of light on some of the details, right? Some obvious restrictions are necessary, right? Like obviously you shouldn't be able to write like operator plus int, right? You can't like override the basic types, right? That would be a little bit silly. Although you kind of want to, because you could like, instead of having undefined behavior for all this stuff, you kind of want to make it all well-defined behavior, and that would be really cool. But like, it's not part of the initial discussion yet, unfortunately. Pointers obviously count as built-in types, so you can't obviously override pointer operations, stuff like that. And of course, in this presentation, I didn't really explore any of the special scoping we can do that would actually make some of the overriding of basic operators work. But that's something that I can talk about later. There was a question.
Yeah, I was wondering about what about plus for pointers, because that's not allowed normally.
Yes, so the reason you can't, and this is what I was talking about with the syntax from here. The figuring out which one of these is the pointers, like if you wanted to say like mlvec2 star as like mark one as a pointer and not the other, right? Then it becomes a question of like, how do you know which argument is supposed to be the pointer one, how stuff like that. Which one are you supposed to be passed by? Everyone's supposed to be passed by value. And how do you know that you're not accidentally overriding like, oh, I overrode plus for like a pointer. And so now every time you try to increment a pointer, it just calls an operator instead, right? And so that's why you can't override this stuff on pointers directly. So the same way you can't override for int, you can't override it for int star or my struct star or whatever else, right? Because pointer operations are still a built-in type, even though it's a pointer to your type, right? Does that make sense? Okay. Yes, no, maybe? Okay, all right. So the good news is that it means we solved the core tension. So, when you have these people fighting about functions and operators, right, and I come in and I say both, that means that rather than getting my butt handed to me, maybe we can be a little bit happier and make progress together. And that's my talk. Thank you very much. Okay, so does anyone have any other questions or comments or things that they'd like to ask about? Oh, yes.
I'm not sure if you mentioned it, but regarding the destructor,
Yes.
going to add the destructor call to the operator declaration?
So the question was, can we add the destructor calls to the operator syntax? Like literally just make an operator like squiggly for like destructors, right? And I actually wrote this question comes up a lot, and so I actually wrote a blog post about this. The short answer is yes. The long answer is yes, but you have a lot of work to do. And what I mean by that is that C does not have an object model, right? It doesn't understand like creation, destruction. If you call exit, it's not required to like clean up anything. If you long jump or even go to out of stuff, nothing in C has a concept of like objects or the object model or like how to create stuff. It doesn't have placement new, doesn't have any of that. So when you get into like destructors, like it seems simple to like, oh, I'll just add destructors to this and I'll have the ability to do the thing that I want to do. But then you have a bunch of other very pressing questions about like, how do you handle having an object model in a language that never had an object model? And that's actually very, very it's very difficult to do thoroughly throughout the language. And so, I wrote a blog post. If you go to the phd.dev, it's kind of ranty because I wrote it because I was in anger because we were discussing operators and people were like, whoa, why don't you just put destructors on it? Like put RII and C, just slap some constructors and destructors in there. It'll be simple, it'll be easy. And then it's like, no, you got to slow your roll. It's a little bit more complicated than that. But yeah, so, you can read the blog post if you want. Again, like it's a little ranty, but it should be fun. Other question? Yes.
Could you do it just for the temporaries that are created by your overloader operators?
So invoke destructors, but only for the temporaries. Yes, we could do that, but again, that's like you're getting like a partial system, right? Like you have destructors, but you only invoke them in this case, right? Like I understand what you're coming from and like why it would be helpful, but it's one of those things where it's like having the system there. Like either you should commit to like making a real system that's integrated with the language, or you should just kind of like leave it alone, right? Again, it's very tempting in passage to be like, yeah, we'll just have destructors for this one case, right? Like it's very small, it's simple, it's tempting, but it's not quite where you want to be, Yes. You first, I guess.
Wouldn't you have the same problem with the temporaries that you have with the operators when you chain functions, basically chain two add functions together and just pass a temporary from the first call or from the inner call to the outer call? They would have basically the same problem.
Yeah.
And so I think in this case, the natural C style of dealing with these types is one step at a time, capture your temporaries and clean them up manually. So the same would apply to operators, right?
Yes, but like that's a choice that you'd have to let the programmer make, right? It's just that you have to, in being thorough, you have to point out that like, hey, this natural syntax you're doing with a big int, right, might not behave the way you expect it to, right? But like, yes, if you make a function call and you chain three of these things together, right, you're going to drop some big ints on the floor, you're going to leak some memory, right? And so obviously the conventional wisdom is don't do that, right? And then, this is where C people come in like, well, if you were just smarter and you tested harder, it'd be better and, stuff like that. But, when you're trying to design things that are a little bit safer, a little bit more foolproof, right, you kind of want to avoid or attempt to avoid some of the problems. So, again, we don't have a good solution for destructors in RAI in C, specifically for objects when they're being destroyed. And so that's kind of why we just have the problem, right?
You don't add that problem with operators, you just keep it, you have the same problem that you have.
Right, you have the same problem. It's just that, again, people kind of expect more out of operators. They want it, like, again, we had this discussion in the committee and people were like, well, I don't like it that I can create this gigantic foot gun. And it's like, okay, but you can do that the normal way too. And it's like, well, I still don't like it for operators, right? Like they're holding it to a higher standard than they would hold the rest of the language. And that's natural because you're trying to put a new feature in it and C is a conservative language. So they'll try to kill you, if you change their precious language. Any deviation from C89 is an affront to Kernighan and Ritchie, and stuff like that. But it's not, again, yes, it is not a new vulnerability. It's not a new problem, but it's still one that, I would expect that a rookie would make that mistake with a big int, right? They would start trying to add stuff together and it would fail, right? Whereas if you show them documentation where you have to do each step individually, right? Like there's less of a chance that they'd screw it up, right? Again, it's still like it's up in the air. It's up to you. Yeah, question.
So this would not match with the checked integers, right? They return the boolean. So you can't just put checked in into the operators.
You could, right? So remember how I did that thing where I did the floats and I did the doubles? Well, you would just do the checked ins, but then you do the checked ins with the structures that return the boolean, right? And so you'd stack them all together like a million times, right? And that's how you would solve that problem. Of course, you run the risk of the same thing with big int, like you accidentally ignored a flag that says, hey, you overflowed. Did you want to stop? Do you want to check me? You want to do anything with that? And it's like you just ran over that information, right? You just dropped it on the floor. So again, it's you have to be careful with it, obviously, but again, this is one of those things that they want. Any other questions? Okay, I won't keep you here. I kept you guys a little longer, but thank you. I appreciate it.